Today we're going to go over some properties of waves. And when you think about waves, you probably think about maybe waves on some water or something like that. We'll get into some water waves, but we'll talk about waves in a more general sense as we move through. We'll talk about a little bit about sound waves, waves on a spring or a slinky or a string or something like that. So stay tuned. Here we go. Okay, so here's an example of a water wave. So we've got something bobbing up and down on the surface of water, and it's disturbing the surface of water, and you see familiar ripples or waves moving across the water. And a new type of a term called a ray. It's not a term, I guess. It's just an arrow. We draw arrows in physics. A ray is a line that indicates only the direction of the wave front at any point where the ray intersects and where the ray and the wave front intersect. So basically, we'll get into it in the next slide here, but it's an arrow just represents the direction that the wave is going. You'll see that when you take Physics 30, you will look at light waves and light like bouncing off a mirror or passing through a lens or something like that, behaving just like a wave. Okay, so speaking about that, waves can bounce off things. In order for us to see something, light hits that surface, bounces off that surface, hits our eye, and then that's how we see it. So sound waves bounce off things. When you hear an echo, for example, that is a sound bouncing off a surface and coming back to you, and you're hearing it a second time. So waves bounce off things, undergo the property or the behavior, I guess, of reflection. So here we've got two rays towards a reflecting surface. So it could be a sound wave bouncing off a mountain in the distance, and you hear the echo, or it could be a light wave bouncing off a mirror. Doesn't matter. Here we've got, let's say here's the mirror, and here is what we call the incident ray. So angle of incidence refers to the angle that the incident ray, this one, makes with respect to not the surface, but with respect to the normal line. What we do is, remember, we learned the term normal force in the dynamics section, where the word normal means perpendicular. So if you draw a line that is perpendicular to a surface, you're drawing a normal line. So the dotted line represents the normal line. The angle of incidence is measured with respect to the normal line. Then the ray or wave reflects off the surface, and then we've got a reflected ray. So incident means coming towards. Reflected ray, obviously, is the ray that is reflected off the surface. The angles at which the ray is incident to the normal line and then reflects, again, angle measured with respect to the normal line, they are equal. And that's pretty intuitive, right? Particles also reflect off things. Like you can bounce a ball off the wall or something like that, or off the floor. So if you, let's say, I don't know, throw a golf ball at the floor, it's going to bounce up again. If you throw it down at a very steep angle, it's going to bounce up at a steep angle. If you throw it at a very shallow angle, pretty horizontal, then it's going to bounce up at that same shallow angle. So that's all this is. Okay. Two types of waves we're going to talk about. Two types of what we call mechanical waves. And a mechanical wave is a wave where the particles of the medium that the wave is traveling through oscillate back and forth with simple harmonic motion, but the energy passes through the medium. So getting back to the example of a water wave, for example, you've got somebody bobbing up and down. So the particles of water, the molecules of water, move up and down, and the waves travel up horizontally. So it's not like a molecule of water starts at the tire tube there and then travels across the surface. They actually just vibrate. Okay, so transverse and longitudinal waves are the two types of mechanical waves that we're going to discuss. So, transverse. A pulse is just a short disturbance, usually just a crest or a trough. So here's a picture from your book. It shows a person moving his hand, is holding a slinky, it looks like. And it looks like this person just moves his hand like that. So out to his, looks like it's left, and then back to where it started. So like that. That's just one short disturbance. So it's a little bump, I suppose you call that a pulse. But let's say he moves his hand back and forth, back and forth, back and forth, back and forth like that. What he's doing when he does that is he's generating a transverse wave. The spring is the medium in which the wave travels through. And notice the relationship between the direction that the wave is traveling and the direction that the person is moving his hand. He's moving his hand in this picture up and down, and the wave is traveling across the screen to the right. So those two directions, vertical, the guy moving his hand up and down, and horizontal, they are perpendicular to each other. So the spring is not actually physically moving to the right. The tines or the coils of the spring are moving up and down. So if you were to like attach a piece of tape here or something like that, if we were in the class, I would do that. And the tape, you would just keep around, and the tape would be moving up and down. The tape would not be moving to the right across the class. So the spring is actually the particles of the medium, in this case, the coils of the spring are moving up and down, whereas the wave travels across the screen to the right, perpendicular directions. Okay, so a few terms. The amplitude of a wave can be used to determine the quantity of energy that is stored in the pulse. So amplitude is represented by this particular value here, A, and a transverse wave is made up of a series of crests and troughs. So here, anything above the median line or equilibrium position here, we'll label that as a crest, and then a trough, and then another crest, and then another trough. Crest, trough, crest, trough, crest, trough. That is a transverse wave. The size of the disturbance of the medium, like how far you move your hand up and down. If you move your hand really far, you're going to generate a very tall wave, and that means that it is a large amplitude wave. If you just move your hand up and down a little bit, a small distance, then you're going to cause very small crests and troughs. So it's kind of like the difference between like a tidal wave, for example, a big wave that you can surf on, versus a little ripple on a pond. The tidal wave's got a very, very, very large amplitude, is very tall. The particles are moving in a big distance. That means the wave is carrying a lot of energy. The energy is big. Whereas a little ripple, only up and down a little bit, the energy of that wave is very, very small because of the amplitude, of a small amplitude. Here we've got a symbol that we haven't seen before. This is a Greek letter, and it is the Greek letter lambda, and it is the symbol for wavelength. The wavelength of a wave is the distance between any 2 points that are vibrating what we call in phase. So in phase means that they're doing the same thing at the same time. So right now my fingers or my hands are vibrating up and down, and they are in phase. So when you have got soldiers, let's say marching, a bunch of soldiers marching, and they're going left, right, they're marching like that. They're all stepping at the same time. We say they're marching in phase. Whereas I've just moved my hands around randomly like this, they're moving around or vibrating out of phase. Students walking down a hall in a school. Imagine that sometime in the future. It would be weird if you were all walking in phase down the hall from class to class. You walk out of phase. You're taking different steps at different time. So any 2 points that are in phase on a wave, the distance between those 2 points is called a wavelength. So basically, simplify it for a transverse wave like this, distance between adjacent crests, so from there to there is a wavelength, or the distance between troughs is also a wavelength, from there to there. So notice the length of this arrow, or this wavelength there, these 2 arrows, is the same as that. Okay, Now, talked about reflection. What if you've got, and I'll try and find a video of this, like I've got to attach them here that I normally show, but I'm not sure if it's online. But imagine you've got a slinky or a string or something like that attached to a fixed point on a wall, and you send a pulse down the string. You just whoop like that. So you've got a crest. So the wave is traveling towards the wall, and waves reflect. So when the wave, in this case the pulse, reflects from the fixed point, notice what happens. It undergoes what is called a phase shift, and it's some terminology that we don't really need to focus on in Physics 20, but essentially becomes inverted. You have a crest becoming a trough. So the wave changes upon reflection. Now, we've covered transverse waves with crests and troughs. Now I want to talk a little bit about longitudinal waves, the second kind of mechanical wave. So in a longitudinal wave, the displacement of the medium is parallel to the direction that the wave travels. So in this case, the guy is moving his hand away from him and then towards him. So when he moves his hand out in front of him, he causes what's called a compression. He basically squishes the coils of the spring that are right in front of his hand. And then when he pulls back again, he's causing what we call a rarefaction. So compression, rarefaction. That is what a longitudinal wave consists of. So let's say he starts vibrating his hand back and forth, back and forth, back and forth like this. Compression, rarefaction, compression, rarefaction, compression, rarefaction. Whereas for a transverse wave, it's perpendicular to the motion of the wave. So we have crest and trough. Here we've got compression, rarefaction. The distance between adjacent compressions or distance between adjacent rarefactions, again, that is the wavelength of the wave for a longitudinal wave. Now for a longitudinal wave, the best example that I can think of is a sound wave. A sound wave, anything that is vibrating in the air generates a sound. Like my vocal cords are vibrating when I make a sound. When you have let's say a guitar or a piano or something like that, the strings vibrate and they generate a sound wave, which is a longitudinal wave. The reed on a wind instrument vibrates back and forth. And that basically acts, the vibrating, let's say piano string, for example, when it vibrating like this, it sort of compresses the air molecules in front of it. And then when it vibrates back, much like moving your hand back, you have a rarefaction. So compression, rarefaction, compression, rarefaction. And then the particles of the air vibrate back and forth parallel to the direction that the sound wave is traveling. And those vibrations are passed from air molecule to air molecule because they have intermolecular forces between them, which you guys learned about in Chemistry 20 if you took it. And eventually those will be incident on your eardrum. Now what happens is your eardrum is it's in equilibrium. So it's basically flat at atmospheric pressure. When you get a region or a sound wave incident on your eardrum, when a compression hits your eardrum, it pushes it in a little bit because it's a region of slightly higher air pressure or density of air. So it pushes it in a bit. And then when you have a rarefaction, it bulges out a little bit and it pushes in, bulge out, push in, bulge out, push in, bulge out at the same frequency that the source of the wave is vibrating at, like say a piano string or something like that. So that in that way, the vibrations are transmitted through the air and then we detect them with our ears. Okay, so getting back to water for a second. Water doesn't stretch like a spring, so the crests are not storing elastic potential energy. It's actually gravitational potential energy, and there is intermolecular forces between water molecules, but it's mostly gravitational potential energy. Actually, water waves themselves are fairly complex, but we're going to simplify it for Physics 20. A transverse wave can only travel on the surface of a fluid, so that bobbing up and down on the surface of the water. sends out ripples or transverse waves across the surface. But if you were to take, like you're dipping your hand, like water, your hand in some water up and down like that, you're sending out ripples. If you take your hand and then stick it underwater and then move it up and down like that, well, what you're doing is actually you're sending out longitudinal waves away from your hand. So if you're moving your hand up and down under the water, you're compressing the water molecules above your hand, and then rarefaction, then compression, rarefaction, compression, rarefaction. You're generating actually longitudinal waves. Okay, so here we've got the formula for today. It's called the universal wave equation, and I'm going to talk about it just briefly for a second. It's basically the speed equals distance over time, but for waves. It is called universal because it can be applied to all kinds of waves: sound waves, water waves, waves in a slinky or a string or something like that, light waves, which we'll get when you guys will learn about in Physics 30. So there's a direct application here from the wave stuff you're going to learn about in 20. You're going to learn about, take that stuff forward with you and then apply it in Physics 30. So I'm going to flip to my iPad here, and then I'll go over the example problem.
Okay, the universal wave equation. Before I go do the example problem, I just want to show you something. That it's basically, I mentioned that it's the speed equals distance over time for waves, and it really is. Remember, in a particular medium, doesn't matter what it is, like a sound wave traveling through air at a certain temperature, or water, or a door, or something like that. The thing that changes the speed of a wave is when it passes from one medium to another medium. It changes speed at that boundary. So when it's traveling through a certain medium, it's going at a constant speed. So in other words, we've got uniform motion. And for a wave, or for anything moving with uniform motion, we can describe that as speed equals distance over time. The distance a wave moves in a certain amount of time, we can use it as this. Remember the term period, capital T. It stands for how long it takes to complete one complete vibration. So time for one full, like we use it in the context of going around a circle, one time for one entire trip around a circle. So for a wave, let's say a guy's vibrating his hand up and down, moving his hand up and down, holding a string or something like that, it would be up, down, and back to where you started. So one complete full oscillation. Just like a trip around a circle is, say you start at the 12 o'clock position, you go around, you end up at the 12 o'clock position. The distance here is the distance the wave moves in one period, and the time of one period. And that, by the way, that's the wavelength of the wave, represented by lambda. So really, for a wave, we can express it like this. The distance is wavelength, the time is period. But that's not what it says up there. It says frequency times wavelength. But we remember that frequency is the reciprocal of period, or period is the reciprocal of frequency. And we can write the above expression like this. Instead of dividing by period, we can multiply by 1 over period. And then remember, 1 over period, that is frequency. So then you get wavelength times frequency. And basically, that is your universal wave equation. Speed equals frequency times wavelength. Okay, so now we'll get to the example problem. The pianist plays a note that generates a sound wave that has a wavelength of 0.680 meters. if the speed of the sound wave in the room is 345 meters per second, determine the period of the sound wave. Okay, so we can use our universal wave equation. We're given the speed and we're given the wavelength. So we can then find the frequency, speed over the wavelength. So the speed of sound given as 345 meters per second. Wavelength is 0.680 meters. That would be the distance between compressions or rarefactions for the sound wave. And you get the frequency to be, I wrote it down there, 507 let's say 3529 hertz. So there's the frequency of the wave. You're asked to find the period of the wave. Well, not exactly rocket science. Period and frequency are reciprocals, so the reciprocal of 507.3529 hertz, meter, and we get the period, rounded off to 3 significant digits, 1.97 times 10 to the negative 3 seconds.
Okay, constant frequency, speed, and wavelength. When a wave enters a new medium, it will change speed and wavelength proportionately. So, for example, like I'm sitting in my den right now, and if one of my kids happens to be standing on the hallway or something like that, they could probably hear me talking in the den. So what that means is that sound waves are starting in the air, and then in order for sound waves to make it onto the hallway, they have to pass through the door. You can hear the sound through the door. So the sound travels from the air, enters the door, travels through the door, and then back out into the air again. So it's going from the air to the door, back out into the air in the hall. So that's going from one medium, the air, to another medium, the door, back out into the same medium, the air again. Okay, the speed of sound, or the speed of the wave, doesn't matter how speed, doesn't have to be sound, but I just use sound for my example, depends only on the physical properties of the medium itself. So when the sound wave that I'm generating travels through the air, it's moving at a certain speed. When it travels through the door, new medium, it's now moving at a actually faster speed through the door because it's more of a dense medium than back out into the air. You're going to learn about waves traveling from one medium to another medium quite a bit in Physics 30 when you look at light waves traveling through different transparent media, like a lens, for example. Like what happens when light travels through a lens? Why does it change direction? Something called refraction. You'll learn about that. But for 20, all we got to remember is that the physical properties of the medium dictate the speed of the wave. So, for example, the slinky, the guy by moving his hand up and down when he's holding the slinky, let's say he took that slinky and he attached a rope to the slinky. So what happens is when the wave travels through the slinky, it's going to be going at one speed. Then when the vibrations are passed into the rope, well, that is a new medium with new physical properties. So the speed of the wave is going to change as it passes into the rope. Right, so that's it for today. There's your homework. Very little for you to work on, just introducing some terms. I'm going to try and find some videos for you guys to watch as well. Looking at waves, it's tougher to me to communicate by just kind of waving my hands around. I'm kind of doing the best I can here. But there's some pages to read and some questions to do. That's it. See you guys.